What you can encounter a lot on the easier side of reverse engineering challenges is an elf that takes input, runs it through some gross looking function, and compares the result to an encoded string. The majority of the time, this complex function can be absolutely maddening to try and reverse, and a huge time waster. Luckily, a method exists called symbolic execution, which allows us to statically analyze the program based on constraints we derive from the binary. Furthermore, a Python library exists to implement this process called Angr. Before we go any deeper though, just a quick disclaimer. I'm not a pro at the tool I'm about to share with you, or the concepts it adopts. In fact, I only just started researching Angr and symbolic execution a couple days ago in order to better my skills in an area of CTFs I wish to improve in. That being said, this video acts as a plastic platypus type learning opportunity, and in making it, I hope to relay all the stuff I've learned and teach you in the process, so that you can get something out of it. And with that out of the way, let's start our path. Angr is an amazing tool, created with Pwn in mind, but before we learn Angr and its very wide array of capabilities, we must first understand a computer science concept it utilizes to help us reverse binaries. Specifically, an absolutely insane concept known as symbolic execution. A very high-level explanation of symbolic execution is that by statically analyzing a program, we can create a system of constrained branches, apply it to our input, and explore interesting execution paths. If that still doesn't make a whole lot of sense, don't worry. Right now, we're going to be talking about everything symbolic execution unapplied to Angr. The process goes something like this. First, we create a symbol, which acts as the input we are trying to find. Think of a symbol as a variable you'd see in an algebra problem. The value of this symbol will be determined as we apply constraints to it. As we go through the program, when we encounter a conditional that affects the symbol, we use it to create a constraint and apply it to our symbol. Then we split the branch in two for both possible paths that follow the conditional. Once we find a branch that leads to a desired execution path, we evaluate the input. It is basically a way to find what input causes a specific path of the program to execute. And although these symbols can have multiple values or even be unsatisfiable, if a challenge was written correctly, it will only have one possible value. There are also lots of tree search type algorithms that symbolic execution may use. However, by default, an Angr symbolic execution engine, it utilizes the breadth first search algorithm. It is also important to note a drawback to symbolic execution. Every time a conditional is encountered, an additional branch is added. This can result in crazy exponential growth for more complex programs that have lots of if statements and if statements within loops. This issue is known as path explosion, and because of this, we want Angr to analyze as little as possible in order to keep states small. Now on to what you came here for, Angr. Angr utilizes 4 dependencies to help run a successful symbolic execution engine. This includes the CLE, which is the binary loader, PyVex, the instruction emulator, ClarifPy, which enables us to make bit vector objects, and Z3, an SMT solver. Angr utilizes a simulation manager, which is how a program is explored and managed. Symbols in Angr are stored in something called a bit vector object, which has the properties of its size and its constraints. Using Angr, we can configure an initial state, which tells us where in the program is entry, and properties such as memory or register values at entry. We can then pass this initial state to the simulation manager and explore until the desired branch is reached or all states terminate. States will be stored and accessed in lists based on their status. We can also manually add constraints to states, which we will cover later in this video. This is especially useful for avoiding path explosion when you can manually see it. Now let's solve some CTF problems. I'll be using the Angr CTF GitHub repo, and it is in the description in case you want to follow along or solve stuff for yourself first. I'll be jumping around a bit in a categorized order, which slowly introduces the capabilities of Angr and how we can inject our bit vectors as we encounter more problems, as binaries can handle user input in their own unique ways. As symbolic execution itself is mostly magic, configuring the initial state with our bit vectors is where most of our problems will lie when writing our Angr scripts. So without further ado, let's get started. Alright, so examining our first program, which is O2 Angr find condition. Just taking a look at main here, we see it's a pretty simple program. We have a printf, which prompts for the password, and then followed by scanf, which will take standard input and save it here. We see there are no format specifiers being provided to scanf, which is important because Angr cannot actually analyze scanf if it has format specifiers. But because it doesn't, we don't have to worry about that. We will encounter that later though. And then we see a string compare to var3c and var28. We see here that complex function is being run through var3c, which is our standard in. So we want to see what standard in will lead us down the branch, which leads to a good job being put to the screen. We don't want to reverse this complex function because if we look at it, it seems pretty, well, complex, and that's really not something you'd want to do. So using symbolic execution, we can examine what input needs to be provided to lead to this specific. We're going to start by importing our libraries for Angr, so import Angr and clarify. Then we're going to create our project. And here you would specify the file name. I'm just using the binary Ninja API since I'm in binary Ninja. And then we're going to create our initial state. We're going to do p.factory.entry state, or you could do blank state if you want. There's also a full init state where it will start from here at start. But I'm just going to do entry state, and I'm not going to provide it any parameters. You could provide it an address for the address you'd want to start for your entry state. If you are making your own symbol with scanf, you'd probably want to start it after scanf. That way your symbol doesn't get messed up. And then we're going to create our simulation manager. Using this initial state. We didn't have to edit the state or provide any symbols or bit vectors to it because by default Angr will use standard in as a bit vector, and it will process that as a symbol. So this is pretty much a baby Angr challenge. With that, we're just going to call the simulation manager to explore. We're going to provide it the address we want to find, and we'll just use the puts good job. We can also provide it paths we want to avoid, and for that I'm just going to use the else statement. It's a really small program, there's nothing really else here, and this shouldn't even really matter because it's so small and the only thing in the else is a puts, but I'm going to provide it anyway. Wait 1 second, and we can see that the simulation manager has one found state. We're going to access that state using simulation manager, and as we said earlier, states are stored in lists by their status, so I'm just going to do found 0. And here we usually access, or we give it the symbol. We're just going to use POSIX and then dumps 0 for standard in. Here we're seeing the standard input from the simulation manager to see what the input we need is. Alrighty. Now we're looking at O3 Angr symbolic registers. The names of these challenges really say what you're dealing with. We just take a quick look at main. We see printf, and then we don't see a scanf, but we see a call to get user inputs. Let's explore that. And we see this time there is a scanf with 3 hex format specifiers, and these are saved to 3 variables. After it returns back to main, we see the complex function is performed on these 3 variables, and that's what leads to good job or try again. Try again is called in its own if statement this time. So because we have to deal with these format specifiers, it means that Angr is not going to automatically parse standard input, and we are actually going to have to manually create symbols using bit vector objects that we used from the clarify library. So where stuff really changes here, I already imported the libraries and I created the project. However, when we are configuring our state, we're going to have to keep some stuff in mind. Let's switch to disassembly view. So after we call get user input, we see that all the input provided for each hex value is stored in a register. We see it's an EAX, it's an EBX, and it's an EDX. If we go back to main, we see that the values in these registers are then stored on the stack here. So there are two ways we could do this. Actually, we could take over these registers before they're moved onto the stack, or we could straight up just inject into the stack after these registers are moved into it. And what we're going to do is we're going to learn how to manipulate registers because it's simpler. We'll get to manipulating the stack later, but for now let's just consider setting EAX and EBX and EDX with our symbols, because we know this is where our input goes. So let's start doing that by creating our entry state. So we're going to do s equals p factory entry state, and we're going to provide it the first address right after get user input. We always want to skip over the scanf if we're not utilizing it, but we want to do that before obviously our user input is interacted with the way we need it to be interacted with. So we need this to happen because that's just how the program works. We're just going to set all these registers to be equal to what we want. So I'm going to put the entry right there, which is after the scanf, which is in get user input and before our registers values are put onto the stack. And then I'm going to start creating my bit vector objects. We're going to need 3 of them for the 3 registers. And the way you create a bit vector object is we just use clarify.bvs. The first parameter is the name we want to give the symbol. The second parameter is its size and bits. These are 32-bit registers, so the size would be 32 bits. And I'm just going to use the same scheme for the next 2. All right, we have all our bit vectors. Next, we're going to interact with the registers using our initial state. I'm just going to do state.regs, and we're going to do the first register first, which is EAX equals password 0. And now that we have set all the registers to our bit vectors appropriately, we can continue as normal. So we're going to create our simulation manager. We're done manipulating the state. And we're going to move down lower to find where we want to go and avoid. This seems to be the block that we go to if we get the password right. So we're going to say sim explore, find here, and we'll avoid the else block, which seems to be starting right here. Press enter. We see simulation manager came back with 1 found and 3 avoid. Now to see the value of our symbols, we're not going to be able just to do POSIX and then dump the 0. Because we didn't utilize standard in, we provided our own symbols. So we're going to have to call solver.eval to evaluate our symbols. So let's do that. And since we have 3 symbols, I'm just going to concatenate them together with a space. So it's in the same format that we would need to provide to the program. As we can see, it's supposed to be each value separated by space. First, I'm just going to show you how to access a symbol using the sim manager after it's been explored. So we do same as we did before, sim manager .found 0 solver.eval. The first parameter will be password 0, which the first parameter is just the symbol we want to solve for, and then we're going to do cast to bytes. And we'll do hex because we know that's what we have to input it as. Alrighty, and that's basically how you do it. Real quick, I'm just gonna do that and separate it by spaces for the other 2 symbols. And this is our key. Alrighty, so now we're on 05 Angr symbolic memory. We see, just looking at main real quickly, that our situation is a bit different, but it's actually easier. We see a scanf taking in 4 strings, each 8 in length. And we see that instead of anything being pushed onto registers, we can just see here in the high level IL that our strings are actually being saved at static addresses. Probably, yes, so it's just being saved at global variables or a global variable. So that's a good thing. We have static addresses, we can just write directly to it. We don't have to manipulate any registers. It's a global variable. We don't have to do anything with the stack or whatnot. So this is actually easier than the last one, which was 03. So we're just going to be exploring how we can interact with the state to write directly to explicit parts of memory. So before we do that, I'm just going to go to the disassembly, and we're going to choose an entry point. We want to do it after the scanf. I'm going to start right here because this instruction after the scanf is clearing or resetting the stack, and we don't really want to do that. We don't need to do that, so we're just going to start at this address right here. So I'm going to do s equals p factory, you know the drill, entry state address equals like that, and we have 4 strings. I'm going to create my bit vector objects. I'm just going to call them s followed by the number because there's 4 of them and I don't want to type a lot. Okay, now that we have all our symbolic bit vectors, we're going to write to the initialization state's memory. So we're just going to do s.memory.store. We're going to specify the address. So I'm going to go back to high level IL and simply grab the address we want to save the first string to, paste it, and then followed by the bit vector or the symbol we're saving there. And I'm just going to do that for the rest of them. Alrighty. So we've saved all the symbols to the correct addresses. Now we're just going to create the simulation manager and explore. And here we have our key. Okay, we skipped over a couple. We'll be going back to 04 after this one. I just decided to skip to 06 because it seems really similar to the last one we just did, where we were overwriting static memory addresses. Here we're going to be manipulating dynamic memory addresses with our symbolic bit vectors. So if we look at the program here, we can see that we have a scanf for 2 strings again, saving to buffer 0 and buffer 1. We can see that we're not being provided addresses, we're being provided variables, and these variables hold pointers because they're equal to malloc, which malloc is a C function that manually allocates space and memory at runtime. So we're not going to have this address until the program's running. But what we can do to overcome this problem is we could write our bit vectors to free space in memory that's not being used, and we can get those addresses where we writ them to, and then we can overwrite the variables of buffer 0 and buffer 1 with pointers that point to our symbolic variables, which are now in memory. So we're going to be doing just that, and the only thing we're going to be using is s.memory.store like we did last time. We're just going to be manipulating memory and changing some stuff. So let's get started. We're going to first define our entry states, and as usual, we're going to want this to be after the scanf is finished doing all its work. I'm just going to go to disassembly, and again we're going to avoid anything that is, resetting the stack or whatever, and we're just going to go to the next one. And then we're going to make our symbolic bit vectors. Alrighty, now we're going to store these bit vectors in free memory. So let's go to the hex editor, and we can scroll down here to what's probably BSS, and we see lots of free space over here. So we're just going to use this. Or I could even do it one more, just to be safe with lots and lots of null padding. So we'll do oh, did I type any? Okay. s.memory.store. Take this address. And here we will store our first symbolic bit vector. And we'll just add 10 to that and store the next one, because we know we got clear space for days. Alrighty, so we've put our symbolic bit vectors into static addresses, which we have access to. So now we want to, overwrite buffer 1 and buffer 0 with pointers to these addresses. So let's do buffer 0 first. We're gonna see that buffer 0 is at this address. So we're gonna do s.memory.store. And then we are going to provide it the address of our first variable, because buffer 0 and buffer 1 are pointers. And we're going to specify the size in bytes, going to be 8. And there we have it. That's our key. All right, moving on, or I guess we're going to move back to 04, because that binary does introduce a pretty important concept. All right, here we are on 04 Angr symbolic stack. Just taking a look at main, we can see this one is pretty different. We do printf enter the password, we call handle user, and it seems that the rest of the program happens in here, and this function is also where it's determined if we do the right password. It's important to note that since we're not returning to main for anything important, and the evaluation is occurring in this handle user function, which is the same place scanf is, unlike where we set registers or manipulate memory after a function is called, we can't just jump straight into the middle of a function and expect everything to be all right, because we've skipped stuff like the function prolog that manipulates the stack, and we'll probably segfault because there's just a bunch of memory exceptions happening. So what we're going to do is, like always, we're going to define an entry state after scanf, but we are also going to manually do that function prolog ourselves, using the register, the s.regs.register name thing we did much earlier when we were doing that challenge where we are changing registers, to manually do that move EBP ESP thing, and then we are going to continue. So let's just look at this a bit closer. We can see that we're doing 2 unsigned integers, and they are also being placed onto the stack, which is further reason we should, do that function prolog manually ourselves. We see that they are being stored at EBP minus 10 and EBP minus C. So, first of all, let's create our state to be after the scanf. So s equals p.factory.entry state equals address, and do right here. And now let's manually do that function prolog. If you don't know it, you can see it up here, but I'm just going to do s.regs.ebp equals s.regs.esp. And there we go, we've done it. Now what we need to do next is, since we are pushing this onto the stack and we just reset the stack, there's no space on the stack. We need to manually allocate that space for these values. Of course, if this was just like a decimal value, we could just subtract that from ESP, since EBP equals ESP currently. But these are hex values. So what I'm going to do is I'm just going to take the lower address, which is OXC, and these are both the same type. So I'm just going to subtract the size of the next type from it, and that should be the amount of space we need. So OXC, unsigned integers, can be 4 bytes. And we need to allocate 8 bytes of memory onto the stack. So I'm going to do that now. We're going to do s.regs.esp -8. And I just remembered I forgot to create my symbolic bit vectors. So we're just going to do that now. Int 0 equals clarify.bvs. Now we've configured the stack the way it needs to be configured. So we can just push these symbolic bit vectors onto the stack using the stack push function. Int 0, and then we'll do int 1. And that should be all. Standard stuff from here. And here we see the 2 parts to the key. We see both integers. So we got the license key. Of course, it's just these 2 things separated by a space. I was just too lazy to print it all out on one line since I got to cast it to integer and stuff. But you get the idea. When we jump in the middle of a function and we remain in that function and stuff is happening to the stack, we need to manually configure the stack. Alright, we skipped one. We're on 08 Angr constraints, and this one's going to teach us how to manually add constraints. So if we take a quick look at main, we can see here at the scanf, we're just providing a string and it's being saved at a global variable. So we can just statically write to that address. And then we seem to have an issue. If we look at the check equals, we can see that there is a for loop with another conditional in it. So just taking a better look at this real quick, this is going to cause path explosion. This seems to be an additional constraint, because if we go back to main, we see there's a complex function here, and it's not anything to do with this. So this seems to be an additional constraint, and the constraint, we would have to analyze this, but it just says it in the function name right here. It checks if the symbol is equal to this string. So that's pretty useful. That's baby stuff. We don't have to look at this. That's good. But it's going to cause path explosion because it's a loop with a conditional inside it. So if you remember path explosion, it's an exponential growth problem. Every time we go through this loop, this conditional is going to be hit, and it's going to add another branch. And it's going to create a whole lot of paths, and we do not want that. So we're going to avoid this loop and manually add our own constraint that does the same thing this loop does. I'm assuming that this loop would have just gone through every character of the input and compared it, but we're just going to add our own constraint that just compares our symbol to this. So what we're going to do first is pretty standard stuff. We go back to main, and we are going to define our entry point after the scanf and save our symbol at the buffer variable right here. So let's do that first. So s equals p.factory.entry state address, and we'll do after the scanf right here. Next, we will create our symbolic variable. And we'll store it at the appropriate address. All right. So what we're going to do is we don't want to analyze this check equals function. So we are actually just going to we're not going to include this in the simulation manager. We will just stop, obviously, after this complex function is called, because we still want to analyze that, and after the scanf, but we'll stop before we reach here. So I'm actually just going to do the one above it. And I'm going to create my simulation manager now. So we see we got one found. That's good. We're not done yet. We still got to do this one constraint here. But we know what this constraint is, so we can manually add it. So I'm going to create another bit vector, and we're going to compare. So what I'm going to do is I'm going to make constrained bit vector equals Symbolic.found 0.memory, and we'll load it from memory. It was at right here, and the size in bytes. So like that. And then we can manipulate the found state and add a constraint to it. Add constraints. That's the function. And it just takes one parameter, which is the constraint or constraints we're going to add. We're just going to do constrained BVC has to equal and we'll just copy the string and take out the first part. And we got to encode it because the constraint BVC is going to be bytes. So like that. We've added the constraint, and now we can just do what we've been doing. Symbolic.found, we solve it, and specify the password, cast 2 bytes. And there we go. That's the key. We manually added a constraint in order to avoid path explosion. So there's that. Alright, so that's all we'll be covering today. I hope you guys learned a bit more about Angr and the core concepts behind its symbolic execution engine. Of course, there are many more challenges in that GitHub repo you can try for yourself. Angr has a ton of capabilities. We barely scratched the surface. There are other challenges in there. For example, one I liked was one that didn't use scanf to read inputs. Angr actually has the capability to simulate a file system. It can make hooks. It can even simulate scanf. So be sure to look through those challenges if you want to learn Angr more in depth and understand its very wide array of what it can do. Besides that, hope you learned something. I'll see you later.